Hello everyone, my name is Dhayalan Shakthivel. I'm a research associate at the James Watt School of Engineering, University of Glasgow. I welcome you all to the presentation. In this presentation, I'll be talking about the kinetic analysis of the VLS growth of semiconductor nanowires. And I'll be talking about two types of nanowires. One is elemental, other one is binary nanowires. This slide explains the outline of the presentation, where I start briefly explaining about the significance of semiconductor nanowires for many different applications. Then I move on to explain the concept of VLS mechanism using a phase diagram and its significance in the one-dimensional nanowire growth. And I'll be explaining about the experimental aspects which need to be considered for the growth of nanowires using VLS mechanism by using interface techniques. I'll be explaining the experimental results followed to that about the elemental and binary nanowires, semiconductor nanowires, and then I'll be explaining about the growth kinetics, including all the atomistic processes. Finally, I'll conclude the work with the major results obtained in this kinetic mode. Nanostructures are broadly classified into three different categories. One is zero-dimensional, two-dimensional, and 1D nanowires. Conventionally, quantum dots and metallic nanoparticles are commonly termed as zero-dimensional particles, whereas atomically thin layered materials such as graphene and MOS are called 2D layered materials. 1D nanowires are high aspect ratio structures whose diameters vary between a few nanometers to hundreds of nanometers. And the research in semiconducting nanowires are obtained in different classes of materials for metals, semiconductors, and dielectrics. And semiconductor nanowires are having significance for various applications, starting from devices, sensors, energy harvesters, and flexible and large. Research in semiconductor nanowires has been carried out broadly in 4 different domains. It starts with the growth and characterization of using different growth processes, mechanisms, and experimental techniques. Major aim of the central part of this segment of the nanowire research is analyzing the chemical and physical properties of the nanowires, especially when they're getting to the domain of sub 20 nanometers, because the properties of the materials are completely changed compared to their bulk when they get into the nano-sized region. And after once we found that there are some interesting physical, chemical, and properties, there will be devices prototypes that will be developed based on these nanowires. And to probe the properties more, to understand the nanowires more, for them to use for many different applications. Once we are able to develop a good strategy for demonstrating devices such as field electronics, sensors, and energy harvesters, then engineering tools will be developed to make devices for different applications. And this involved, we are fabricating the nanowires at very harsh conditions such as acid etching and high temperature processes. These are all kind of experimental conditions. So we need to have strategies to transfer those nanowires onto different substrates so that it can be fabricated over large area for different applications. So the engineering tools development and transfer processor development comes in the third category. And using this thing, combining these three, we'll be able to find a lot of applications for semiconductor applications such as in large area electronics, flexible displays, energy harvesting, nanoelectronics, and many more. And the significance of the nanowires are, importantly, these nanowires are single crystalline in the dimensional range of a few nanometers to even up to a few microns. And we have developed so many techniques, experimental techniques, so that we'll be able to control the dimensions accurately with accurately controlled composition of techniques. And importantly, we can engineer the material so that we'll be able to produce nanowires with heterostructures, meaning that we'll be able to produce nanowires of core shell, axial heterostructure, p-junction based gradially varying nanostructures. We'll be able to produce structures. And moving towards a promising growth process which has been explored widely for the semiconductor nanowires material study, which is Vapour-Liquid-Solid growth mechanism. On the left, I'll be given the schematic picture of the to explain the conceptual picture of the kinetic. That is, when we are having a catalyst particle in a very controlled ampere at above the temperature of 500 to 1000 degrees centigrade, the catalyst particle are placed at the controlled ambient. We will introduce a gases or gaseous sources into the ambient. Suppose we want to grow a silicon nanowire, we'll place a gold catalyst under very controlled ambient in the hydrogen flow. We'll introduce the silicon sources such as silicon tetrachloride. This flux will get injected into the catalyst particle through vapor, from vapor phase to the solid catalyst particle. This solid catalyst particle will get converted into a liquid and get saturated with silicon. And the saturated silicon will try to come out of the catalyst particle at a preferential location. So the energetically favorable location is the interface between the catalyst particle and the solid nanowire, where it gets precipitated. So the precipitated wire possesses a diameter of the catalyst particle, which will become a nanowire over prolonged time. So the choice of the catalyst particle can be decided by a binary phase diagram. If we want to grow silicon, we'll be using metals such as gold, platinum, copper, aluminum, whichever compatible for the particular process applications. The SEM images in the lower right hand corner showing the typical image catalyst particle and the wires grown using VLS mechanism. The silicon analysis has been shown. The significance of this mechanism is any material, any composition, or any size diameter can be grown. There is no limitation. Only requirement is we need to find appropriate phase diagram for the nanowire to be grown, so that we will be able to grow the nanowire of the required diameter. And this briefly explains, the schematic briefly says what kind of experimental setup will be used for the execution of VLS mechanism using vapor phase techniques. This vapor phase techniques commonly termed as chemical deposition, metal organic chemical deposition, and vapor phase transport. Any technique used for the growth of nanowire, which depends on the final end material. For example, if we want to grow SiOx nanowires, we will be able to grow vapor phase transport method. And depends on the requirement, we can use any kind of source from gaseous, liquid to solid sources, which need to be properly transported into the growth field. Suppose we want to grow silicon nanowire, we can use, if we're using a silane gas, we can use silane gas connected to the growth friend, the gas manifold, mass flow control. If we want to use a vapor phase transport method for zinc oxide, we can place the sources inside the close to the substrate where it is evaporated using high temperature and it transported to the growth friend using carrier gas. And vapor phase transport methods are promising because they provide the sufficient temperature to grow single crystalline nanowires of a particular requirement. This slide explains briefly how the diameter of the nanowire decided by the catalyst particle, where on the top left image shows a sub 20 nanometer catalyst particle, which used to grow silicon in the sub 20 nanometer chain, where 100 nanometer around catalyst particle has been used to grow silicon nanowires using a CVD approach. And this slide gives the SEM images of amorphous and single crystalline nanowire for comparison using VLS mechanism. For the amorphous growth, there are only two amorphous nanowires grown till date: the silicon dioxide, ammonium oxide. Those are grown using a VLS mechanism, and a solid sources like thin films and silicon vapor, where the silicon wafer is coated with a thin film of gold as well as nickel, and nickel will enhance the vaporization of silicon, so that it gold get absorbed over the gold catalyst particle, and so that it will result in a silicon anode. On the top right, on the top A and B image is showing showing the catalyst particle, and the C and D showing image C shows the single crystal, and it has a straw cutter, which is a straight wire, and which is grown straight with respect to the substrate, and the image D shows the amorphous silicon dioxide wire grown using VLS, which is end. And the statistical analysis on the lower left corner shows wire diameter corresponds to the size of the catalyst particle. Having grown two different materials, silicon elemental and binary, now we are explaining about a kinetic model which is able to predict the growth rate of nanowires without which is well within order of the experimentally measured value. In this thing, we are analyzing the VLS process using various atomistic processes. The atomistic processes are divided into two parts: one is injection, other one is ejection. Injection refers the injection of flux into the catalyst particle getting saturated, and ejection refers the out of the silicon elemental silicon coming out of the catalyst particle using different processes. And we are able to injection is divided into two parts, where the silicon getting injected from the vapor to liquid, or it's getting absorbed over the silicon solid silicon surface, diffused into the catalyst particle. At steady state, the rate at which the injected atoms getting into the catalyst particle is equal to the rate at which it is coming out of the droplet. And by developing various expressions, we are able to predict. And in the left side, we have shown that the predicted growth rate of nanowires fall within the order of magnitude, which is compared with experimentally reported, which is widely reported in the literature, where growth rates varying between 1 to a few hundreds of millimeters per second. And if we're extending this growth model towards binary nanowires, we need to add one more additional step in the process, where after the crystallization process, it going through oxidation. This oxidation is entirely different than the conventional thermal passive oxidation happening at high temperature or low temperature. So at steady state for binary nanowire growth, the rate at which the crystallization occurs will be equal to the rate at which the oxidation occurs. In this two process has been evaluated using suitable expressions, where the growth crystallization is expressed with dependent on nucleation frequency, which includes all the atomistic processes, all atomistic parameters such as energy barrier and the supersaturation. And the diffuse oxidation involves the diffusivity. These are atomistic processes, atomistic processes and atomistic parameters which cannot be measured directly, but we have connected these parameters with this model to state the growth rate of nanowires. Here we have explained the growth rate prediction using the kinetic model, where initially we have estimated the supersaturation in the droplet during the growth of nanowire using the steady state kinetic balancing for different sized catalyst particle. And using this, we have estimated the growth rate of nanowire for different diameters, and oxidation as well has been observed. And the oxidation and crystallization rate are observed to be fall in the same order or close to the experimental values, which we have measured experimentally using nanowires growth in the VPT method, and we have compared with the experimental results. And what we have, the key finding is we are able to compare the atomic parameters, dissolution energy barrier and supersaturation, with respect to connected to macroscopic parameters such as pressure, temperature, and catalyst diameter. And I would like to conclude the work with highlighting the major outcome of the kinetic model of the nanowires. And we are able to grow elemental and binary semiconductor nanowires in the sub-100 nanometer region. And the kinetic model is able to connect the atomistic parameters with the macroscopic parameters. And we are extending the model to other binary oxides. I would like to thank my team members for the positive contribution in technical discussions, as well as experimental contributions from these team members. I'd like to thank the funders of research, the SRC, Open Commission, and the Royal Society. And I'd like to take this opportunity to thank James Wagner Center for helping us to carrying out the experimental fabrication work. And I thank everyone who listened to the talk, and thanks for your attention. And we would like to take part. If you have any queries, feel free to contact us through my ID, as well as you'll be able to reach us through social media and other sites. And I will thank you again for listening to the talk.